So thank you for joining this panel. I'm so excited about the group of people that we have on stage here today. We have two of Forbes 30 under 30 under one roof here on this panel, and a researcher from a global corporation, Fujitsu. And all three of them are going to talk about the way that technology can help provide universal access for people with various kinds of differences in neurodiversity. Dr. Cong Chen is a member of the research staff at Fujitsu Laboratories. His research interests include intelligent human-computer interaction, information retrieval, and information visualization. At Fujitsu, he created guided play, which is a technology he will tell you about today. It aims to evaluate and improve children's play behavior, especially for those with autism. Cong has a PhD in computer science from the University of Texas at Dallas. Please welcome Cong.
All right, good afternoon, everyone. I'm a researcher at the Fugees Lab. Before I started talking about the project of guided play, let me give you some introduction of Fugees Labs and the group I'm working on. So Fujitsu is a leading IT provider in Japan, also a major player in the globe. To help it develop the development of its future technology and products, Fujitsu has R&D centers around the globe in China, Europe, and in here. Our main location in US is just 10 miles away with about 30 researchers working on the full spectrum of ICT, including optical networking, security, healthcare, and education. So I'm part of the Digital Life Lab. The mission of our lab is to enable humans and the computers to interact with each other and work together in this machine dance world. Here, the machine can be a hardware, a sensor, a software, and apps. Imagine how many apps you have, and then you have so many access to so many machines at the back end. So with the sensors and the analytics, today's ecosystems are becoming more and more digital and distributed. Take healthcare, for example. Instead of being delivered only in a hospital, we can have access to healthcare anywhere you want, and even personalized based on your personal data through mobile sensors. So this change from analog and centralized to digital and personalized is happening in almost all the ecosystems. And obviously, machines are getting more and more intelligent. Before they evolve themselves into Skynet and kill us all, there still be around a period of time that humans play an important role in those ecosystems, such as making decisions. So in our lab, we want to utilize the cognitive and data science and build systems that support the collaboration between human intelligence and machine intelligence. The main themes in our lab include personalized interactive assistants and human-machine hubs. So here are some examples of our project we've done recently. Lifeboard is an interactive and a personalized visualization that help people to take actions and have better outcomes for wellness. So it utilizes the concept of scarcity, which means something important for you, but it's getting less and less. So to persuade people to take actions and in order to reach a better outcome for healthcare. And one is a service that is already available in the Android marketplace to help you reach your bigger goal using micro goals and social support. And also, Coach M is a machine support for human therapists, human coaches to interact with your end users. And finally, we started the project of guided play at the second half of last year, which aims to develop intelligence behind a game or toys that can understand the repetitive behavior often seen in children with autism, and also teach them how to play in a more typical way. Okay, so let's talk about play. Especially for young kids, play is what they do, right? It's like their second nature next to sucking. And they learn almost everything during play: language, emotional, social, and motor skills. Unfortunately, some kids have some impairment in their play skills. One example is children with autism. One of the core symptoms of autism is restricted and repetitive behavior. So you can see this in their body movement, like hand flapping, rocking, or their repetitive language, or the way how they play with objects in the games. So this would potentially limit their possibility to play with typical peers and learn from them and develop various skills such as social communication. So this has a huge impact on a child's development. And there are basically two parts of the story. One is recognize of the red flags and the evaluation and diagnosis, and the other one is the intervention. Well, we all take data about our child, but in current common practice, we typically take data about the physical development, like height and weight of the child, and ignoring many aspects of the critical development of the child, such as emotional, social, and intellectual development. And even for physical development, we have to go to a doctor to manually check the data. And on the other hand, parents are not always have the experience or sensitive enough to notice the early signs of autism or other developmental disabilities. And that explains why even in US, the gap between parents noticing something wrong to finally getting a diagnosis of autism is about 2 to 3 years. And there are so many things we can do in 3 years, especially in the early stage of the life. So this can eventually help to lower the cost and increase the outcome of the treatment. If we have the data, actual research have shown that based on the manually observed repetitive data of the child, machine learning can actually precisely predict later diagnosis of autism. So if we've had the data, we can act early and do a lot of things. And of course, it's unrealistic to ask a parent to observe the child's play 24 hours to see, hey, my son has been playing the blocks always in the same way for 30 minutes. There must be something wrong. Let's go to see a doctor. But machine can do this. Right? Machines are more sensitive, and it can collect a large amount of data and compare with other peers. Okay, another part of the story is intervention. So the majority of treatment of autism is based on behavior analysis. So this chart shows the model of floor time in which a therapist would first observe the child's play, and when she noticed something wrong, she would join the child and follow the child's lead, doing whatever the child is doing. The idea is that nobody wants to be changed, even kids. So the first priority of the business is to be a part of the team, to do whatever the child is doing, so the child will accept you as part of the game. And then it's tricky. The part is that the therapist should have the ability to notice a good opportunity to introduce a small change into the activity and making it fun, so that the kids will accept that, okay, it's fun to make some changes in the behavior, and eventually will accept this change. And this will conclude a one loop of the interaction. Obviously, this intervention is very labor-intensive, very expensive, especially when you want to do 20 to 30 hours a week. So we are hoping that technology can play a part in this part of the practice. That's why we are creating a guided play. The goal is to develop the intervention, assessment and intervention technology behind a game or toys that can serve as a co-therapist. So it can observe the child's behavior and take some measurements of the development, and probably can detect some abnormalities, and can be a part of the treatment program that can implement those what human therapies are being used in their treatment. And we started building our system based on building blocks. The reason is, first, blocks are always one of the first games young children are playing with. And the second reason is researchers have shown that block play is highly related to various aspects of child development, including social cognition, math, fine motor skills, even social communication. And from a technical perspective, we found that while block play is highly structured, there are only limited ways you can do with one piece of block. So in that case, a machine can precisely model what the child is doing and run all kinds of analytics based on that. We figured that there were two ways to implement the technology. One is based on digitally enhanced physical blocks. So imagine if you can, well, they have been already doing this, put sensors into the blocks that can detect the locations and the movement of each pieces. We can detect repetitive patterns during the child's play. And it's also possible to make the connections programmable so that we can disable some of the connections as a way to dissuade undesired behavior, and also enable new connections as a way to provide a prompt of playing in a different way. And of course, we have building a reward mechanism in there to encourage positive behavior. What we are doing right now is implement the system using a software because it gives us more flexibility. So when it detects a repetitive pattern, the system can generate a background theme and an outline of the target shape. So instead of building a line, how about we make something a little different, like say a car? So the child can fill in the blanks and eventually finish the construction. And then we can immediately change this into a live object using animation, sound, whatever motivates the child. So this way, we're using basically the same principles of behavior intervention to teach the child to play in a more flexible and a variable way. So we implemented it as an app in iPad, which will be soon released to the App Store. You can download it for free and try it. So it allows the child to play freely using digital blocks and build all kinds of constructions. And at the back end, the parents can see what constructions the child has made along with the time, as well as some metrics about child's behavior, including the variability of the constructions. Are they always the same thing, or are they very different? And as well as the categories of the structures. There are some houses, there are some animals, there are some planes. We can categorize the structures. And there are also some measurement about the complexity of the structure, such as the size, dimension, or the symmetry of the structure, because they are related to the stages of the development. And we have started recruiting participants to run a clinical trials with CARD, Center for Autism and Related Disorders. We're trying to see how our system would play in their existing practice of their behavior treatment. Even before we have a full range of data, our initial experiment with those kids have found several interesting findings. So first is, those kids are really smart. Even very young kids, like 2-year-olds, can figure out how to play with a game. They can also figure out how to crash our system as well, because sometimes they tend to play in an unexpected way, like always pressing the home buttons. And also, another interesting thing that is really inspiring us, we found a highly synchronized behavior between physical world and the digital world. So when a child is building something in the digital game, we found actually he has been already making this in using physical blocks. But that means what we are teaching the digital system may have a real impact in their real life and may even generalize to other activities. So currently, we only tested on blocks, only one toy, only one activity. Probably doesn't, it's not enough to tell anything whether this child has autism or not. But imagine in the next few years, we'll get more and more such smart games and toys in a child's everyday activity. And then it's possible to build a set of testing and treatment instruments like doctors do to diagnose a child with autism. In that case, we can use them as a screening and intervention tools for professionals and teachers. And we're also interested in testing this technology into other populations, such as seniors with some mental disabilities. And also, I think it's also possible to utilize the system as a platform for personalized treatment. So content creators like game designers, therapists can program the system, program their treatment goals into the system, And the users, parents, can download the lessons based on the child's individual needs. So in that case, we can build an entire ecosystem that benefits all the stakeholders in this community. So that's our project of guided play, and I'm hoping to listen to your comments. Thank you.
So I'm very pleased to introduce our second panelist, Haben Girma. She is a White House Champion of Change, a Forbes 30 Under 30 leader, and a BBC Woman of Africa hero. She's the first deaf-blind person to graduate from Harvard Law School, and today she works as a civil rights advocate for equal access to information for people with disabilities. She's earned recognition from President Barack Obama and President Bill Clinton, and had the honor of introducing President Barack Obama and Vice President Joe Biden at the White House celebration of the 25th anniversary of the Americans with Disabilities Act. Among her work, she increased access to a library of digital books for blind readers in a 2014 landmark case. And her TEDx talk, which highlights her work, continues to inspire people to strive for a more inclusive society. Her associate, Matt, will be typing the questions after her presentation. And so when you guys do have questions, just speak slowly so he has a chance to type and ask. And I will be pressing the buttons to advance her slides. So, Haben, you can go ahead.
Thank you for the introduction, Karina. Good afternoon, everyone. My name is Haben Girma, and I work as an advocate for people with disabilities. Technology has facilitated many opportunities for people with disabilities, including me. I'm deaf-blind. Deaf-blindness encompasses a wide spectrum of vision and hearing loss. I have a little bit of vision and hearing. I see maybe about 1% of what the average sighted person sees. And I identify as deaf-blind to signal to the world, use non-visual techniques and non-audio techniques to maximize our ability to communicate. One of my best friends, when she first met me, wasn't sure how to say hi. She was sitting next to me at one of our classes at Harvard Law School, wondering what to do. She waved hi, and I couldn't see it. She voiced hi, and I couldn't hear it. It was our first day of international law class, and she wasn't thinking about international law. She was thinking about how to get my attention. And partway through the class, she came up with a plan. She went onto Facebook and sent me a message saying, "Hi, Haben, I'm sitting right next to you." I actually don't check Facebook in class. But I reached out afterwards when I saw the message and explained the different technology I use, the different systems I use to communicate with people. Technologies that are designed with access in mind can be used by people with disabilities, and we need more developers to program their websites and apps so that people with disabilities can connect with friends, engage in school, and be part of the workforce. When people meet me, the first question is usually, how do you communicate? The second question is usually, have you heard of Helen Keller? The next slide. Yeah. Helen Keller is an amazing advocate. She lived from 1880 to 1968. She advocated for women's rights, for workers' rights, for disabilities, and many different groups. She spent her whole life advocating. Yet many stories about Helen reduce her life to one theme. She succeeded despite her disability. Disability never holds anyone back. All the barriers that exist are created by society, and it's up to all of us to work together to make sure those barriers are dismantled. Helen was successful in large part because she found herself in communities that were inclusive. She went to Radcliffe College. Radcliffe ensured that she had books in Braille, that she had interpreters in class. Harvard wouldn't admit Helen. Harvard back then was only for men. Her disability didn't hold her back. Her gender didn't hold her back. It was the community at Harvard that made the decision to exclude women. As another example, Helen's community wouldn't allow her to experience marriage. Helen fell in love, secretly got engaged, but her family forcibly prevented her from marrying the person she loved. Her disability didn't stop her from feeling love. She wrote extensively about love, but her community, her family, created insurmountable barriers. All the barriers that exist are created by society, and communities have the choice to dismantle these barriers. We've come a long way since Helen's time. More and more communities celebrate diverse relationships and unique families. Harvard eventually made the smart decision to open its doors to women. And now we have many technologies with the potential to create more opportunities for people with disabilities. Next slide. Technology comes in many different forms. This photo shows some of the technology that I use. In the photo, I'm standing at a table reading from a digital braille display. There are about 100 different kinds of braille displays. The way these devices work is mechanical pins pop up to form braille letters, and I read the characters with my fingers. Braille is a tool, not a language. I primarily use English Braille. I can use Spanish Braille, and I've seen Braille in many different languages. I was on a Greek ferry once, and I got lost because all the Braille was in Greek. Braille exists in many different formats, and these devices help produce Braille. In the photo, President Obama is standing at the table, and he's typing on an Apple QWERTY keyboard. What he's typing is being sent via Bluetooth to the digital Braille display. And this is a communication system that I developed. Deaf-blind individuals, deaf individuals have been developing communication systems for years. There's a variety of different communication systems. There's sign language, signed in the air, visually. There's tactile sign language. My brother's deaf-blind, and he will hold his hand over my hand and feel what I sign. And when I'm listening to him, I'll put my hand over his hand and feel what he signs. Other people use print on palm, where they write characters on the palm, the characters in their language of choice. It could be Chinese characters in Mandarin, or it could be in Arabic characters. It all depends on the community. The deaf community is very diverse and innovates new solutions, new technologies. And when developers design their technologies to be inclusive, more people can benefit from these services. So this technology is one example of what I use and what the deaf-blind community has produced. There are various different features that help the disability community. Can we move to the next slide? And the next slide shows accessibility features. One example is screen readers. Screen readers take graphical information and convert them to speech or digital Braille. When web developers or app developers design with screen reader access, the blind community can access the information through their screen readers. The screen reader developed by Apple is VoiceOver. Others include JAWS, Window Eyes for PC. Lots of different solutions out there. Another thing to keep in mind is captioning. Captioning ensures the deaf community can access the audio content of videos. Support for assistive devices like digital Braille displays and switch controls. Switch controls benefit individuals with limited mobility. Maybe someone doesn't have the ability to use a mouse or keyboard. Having support for switch controls can ensure that person can access the information on the website or app. There are guidelines out there to help developers who want to ensure their apps or websites are accessible. The Web Content Accessibility Guidelines. For mobile apps, turn to the Apple guidelines for iOS or Android guidelines for Android. Designing accessibly is a community effort. We need everyone to serve as advocates. Helen Keller was successful when communities chose to be inclusive. And I think the tech community can also make similar decisions and strive for inclusion. Next slide. So when thinking about advocating for inclusion, one thing to consider is planning for inclusion from the start. It's easier to plan for accessibility to ensure your end product is accessible if you plan for it to be accessible. Imagine someone building a skyscraper, realizing they forgot an elevator, tearing down part of the skyscraper, and then installing an elevator. It's more cost-effective and saves time to plan to have the elevator from the start. Same thing holds in the digital world. Engaging with the disability community helps ensure accessibility. Include engineers with disabilities, designers with disabilities, testers with disabilities. That'll help ensure accessibility. Thinking about disability drives innovation. A lot of the technologies that we have today have been designed in part because of disability. One of the first working typewriters was designed by an Italian named Turri in 1808. And he designed it because his blind lover couldn't write him letters. So he wanted to build a device that would make it easier for her to type without being able to see what she was typing. Many years later, around 1877, Alexander Graham Bell was doing research for the deaf community, and in the process, developed the telephone. When you think about new ways of accessing information, new ways of engaging with the world, you design new products. You spark innovation. So keep innovating. Keep thinking about new ways for people with disabilities to use technology, and in the process, you'll build the next telephone, the next typewriter, the next cool new device. Next slide. So if you have any questions, I'm happy to take them now. You can ask me here or later after the presentation, or send me an email at contact@habengirma.com. Thank you.
Thank you. Catalin is a student here at Stanford University. He's a student entrepreneur and the founder of the Stanford Autism Glass Project. He also founded the computer vision company Sensient, which has been acquired by Gaia Systems in 2015. Before he came to Stanford, Voss built a mobile payment system at Pay Near Me while he was still in high school. He's been recognized with several awards for his work in industry and as an entrepreneur, including the Lemelson MIT Prize, Forbes 30 Under 30, Business Insider's 40 Under 40, and several profiles in various media outlets. Voss is a venture partner at Axel Springer, Europe's largest publishing company, and he's going to talk to us about Autism Glass.
Thank you so much.
Ooh.
All right, I mean, I really don't know how to follow that. I have a lot of questions, and that's quite amazing. It's a huge honor to be here, so thank you so much for letting me be part of this. Let's see, so I'm going to start by telling you guys sort of a brief story. I guess as the second autism-focused project on the stage, I'll cut some parts out of it. But this is a story of somebody who's very dear to my heart and goes in a little bit of a different direction. This is David, and like 1 in 42 boys in the US right now, David has autism. And so one of the things that he struggles with are faces, recognizing social cues in people's faces that we take for granted. He actually had to learn throughout his life. And his dad recalls this beautiful story of how every evening before the family went to sleep, they all got together in front of the bathroom mirror and everyone sort of made different faces. And as they were, as they were brushing their teeth, they were sort of the one to pinpoint them out. So this is a beautiful example of how learning facial expressions can work. But the reality for a lot of children with autism today is unfortunately quite different. The prevailing approach to doing this, we've heard a little bit about this, in behavioral therapy today is using flashcards, essentially. People look at happy, sad, angry flashcards. And the problem, of course, is that the way that I smile and the way some girl on the flashcards might smile are quite different. And it's often hard to take that learning into the actual situation. And so what we propose is we've developed basically a wearable aid that runs on a pair of smart glasses, like Google Glasses. And you put them on, and essentially we use the outward-facing camera and some computer vision technology to track faces around you, identify expressions in them, and give you social cues right then and there. And so normally at this point, I kind of show you a live demo of this. But I don't know if you guys have seen, Beth and Jenna are actually back there, and you can just go try it out for yourself and see sort of all the computer vision tech that's behind it as well. So let's keep going here. This clicker is not my friend today. All right, so behind all of this, of course, there's a bunch of face tracking technology that tracks up to 100 points depending on configuration, extract features, and then uses a machine learning classifier to decide which emotion we're currently seeing based on training on a couple of hundreds of thousands of images. We've sort of developed a couple of methods that take technology that people commonly use in academics and in facial expression recognition and move them to the real world application. To give you a concrete example, this is a system that we built, we call neutral subtraction, which essentially allows you to learn the difference between a person's neutral face and their expressive face. And so put that in simpler terms, just because grandpa has a brow furrow doesn't mean he's always angry, right? And so we now somehow need to, when we see a new individual, adaptively learn to recognize their neutral face in real time and adapt to them specifically. We've also developed some approaches that we believe will enable us to sort of scale this way bigger with a lot more social interaction data, including an approach based on convolutional neural networks that basically allows us to create a more granular taxonomy of facial expressions based on sort of less strongly labeled data that we can get back as the system gets used throughout the study. And so with the path forward there, we've started to build active learning systems that enable us to calibrate on any one individual family. So the system will basically query you until convergence to make certain faces or to give it more data of certain facial expressions until it realizes that it's trained sufficiently and it works pretty well. And so to actually take this and integrate it into the real world context, it doesn't quite suffice to just, build a system that gives you some words and that's kind of it. When you actually put it on a 6-year-old, they're probably not going to be able to read this disgusted, right? So instead, you might want to say yuck. And so there's a whole bunch of interface choices that fall into this that we have to deal with. And to make this work in real time, we've basically designed a system that is built around, of course, in the center, a pair of wearable glasses, and then a study app on a smartphone that sort of runs the whole process. And the glasses are connected to provide a variety of different sensors, and we built some of them on top of it, including full field of view eye tracking. But they have the outward-facing camera, the microphone, and so forth. That data is streamed to a phone, which does all the processing, handles all the interfaces, handles the interaction, and then it provides an answer in the form of a social cue that you might receive either via audio feedback or via visual feedback as part of the glasses. And so to give you an idea of one component in this, really the core piece of it that people are using now is the study app. That's where everything begins. That's where you start your new sessions throughout the day. That's where you start your training sessions, and that's where all of your data goes. And so to integrate this more into the context of actual behavioral therapy, one of the things that we've done is we've realized that if you use this device throughout the day and you gather data on people, we know that moment where dad got angry, right? And so we've designed interfaces that enable you to jump back to them. And we call this the parent review interface, and basically review a different moment and say, well, what went wrong here, right? What worked here, or what didn't work, and essentially talk through it again. And then on the glass end, as I mentioned, there's a variety of different ways that we could convey feedback. The easiest ones are, of course, words, but that might not be the best one. There's some work in color research that seems to indicate that colors you sort of notice more peripherally within your field of view. And so we're experimenting with that, with emoticons, all the way to sort of letting children design their own interfaces. And I mean, you could go entirely crazy here, right? It turns out, these kids tend to love technology, and so the idea of designing something like this on their own is something that seems very attractive to them usually. And so to give a summary of that, before I talk a little bit about how we evaluated this, is we sort of have this collection of different sensors, right? There's inward-facing eye tracking, there's outward-facing expression tracking, or head tracking, a microphone, things like that. And so we hope to integrate these sensors using a machine learning system that we built to arrive at real-time social cues that are relevant. Right now, those are simple expressions, right? It's telling you that somebody's happy, sad, angry, and so forth. In the future, we think this might lead to more complex social cues. So to give you an example, David loves talking about trains, and maybe at some point I don't want to hear about trains anymore, but he tends to miss that moment, and he keeps talking and talking and talking. And what should happen is, as the system monotonically realizes that I'm making less and less eye contact, I'm paying less and less attention, and maybe I'm starting to take my phone out and look at it. What it should really do is it should realize that David's monotonically speaking and say something like, pause, ask a question, right? So that's one side of it. And then the other side is that as we're using it, we gather all of this real-time feedback and all of this real-time data, right? And so in behavioral therapy, we hope to integrate those in the form of quantitative metrics. So we can tell week over week in one domain how much more eye contact you're starting to make, how much more you're engaging with faces, how much more you're looking at mom when she talks to you. And we can bring those as quantitative metrics to the existing program of behavioral therapy. But we also put the data into the hands of parents and caregivers so that they have the opportunity to essentially design their own therapy. And we believe that bringing this process out of the clinician's office and into the daily life of people will eventually enable us to build a learning aid that they can, after a limited and self-directed sort of period of use, take off again and unlock their ability to learn in the future. Okay, so we've evaluated this in a 40-person in-lab study. That's where we originally started, here at Lucia Packard Children's Hospital, 20 kids with autism, 20 without, and have shown some quantitative gains using the device over just a short period of time. But I think the more amazing finding of that was that children came back and really loved using the glasses. And so we've expanded this to a much larger 100-person at-home trial, where kids with autism actually get to use these devices every single day in their homes. And we're starting to see some good quantitative feedback from that, but we're still in the midst of it. And rather than sharing that, I wanted to pick out, just couldn't help but sort of share one of the early pieces of feedback of the more qualitative sort that we got from some of the families. And so this is an email that reached us just a couple days into the study as we kicked it off a couple of months ago from one of the mothers who was participating in it. And so let me just read this out. She writes that, "We already noticed something very dramatic that I'd like to share. My son is actually looking at us when he talks through Google Glasses during a conversation, and it was noticed without glasses from his teacher in language art yesterday. It's almost like a switch was turned. Thank you, my son is looking into my face." That's pretty powerful, right? And that's kind of what we did this for. And then to give you just one more example, this is Gabby, and she's a little bit older, but she writes how she's been able to use the learning of the device that she's had with her own family at home and apply it to situations with her friends at school and places like that, and recognize when somebody got angry and asked them what happened, right? Okay, so we still get to quantify that learning, and there's a lot of work for us to do. But some of the kids that sort of wrote to us and talked to us about their experiences in the study also mentioned that, that maybe the emotions that we currently provide them with, maybe the feedback that we currently provide them with, is not exactly tailored towards what they want. And so what do we do in that sort of situation? How do we move beyond sort of the primitive approaches of expression recognition tech that we know today? Well, we believe that the way to do that is not going to be using conventional machine learning. The problem is that when you're starting to personalize to an individual and capture more subtle cues and things like that, it's not going to suffice if you want to detect that, say, somebody's anxious or something like that. You can't just get 1,000 anxious people into the lab and gather data from them. That's just not going to work. And so instead, what we propose is to close the human feedback loop in our system and actually gather data while training and while using it. And so in machine learning, people call that active learning, and we sort of believe it's going to be the future of everything. And so the way that we would like to frame this is, the way we think about our system at a high level is it's kind of a therapeutic tool, right, that gathers data while treating for research, improving the AI, effective computing in general, and a tailored therapy interactively with the user. And that AI system then uses the data to calibrate and adapt as the user interacts with the system, but it can also extend and learn new tasks from the data beyond what we've originally intended it for. Right? And so that last bit is really the active learning one. And so, as I mentioned earlier, we've developed some active learning approaches that enable us to pretty quickly train on given individuals, and some unsupervised techniques to allow us to identify certain characteristics about them in real time. But one of the things that I thought was kind of interesting I wanted to bring up is, we sort of believe that this could be a broader framework for active learning in personalized medicine, because as Gabby starts to use his data, or as David starts to look at his own data, he can go to that video and figure out the moment exactly where something happened that he cared about. He can start that moment, he can write a comment about it, and that closes the feedback loop. We get that information back, and we're able to use it, in some sense, as semi-supervised training data. And so we believe that this will extend beyond autism itself, and that sort of doctor-patient device interaction provides for a very rich context for that sort of machine learning where we loop the human into the feedback equation. And from our perspective, autism is really just the beginning, right? People with schizophrenia, post-traumatic brain injury, addiction, depression, anxiety, we think could benefit from this type of aid. And we sort of treat it as a very broad paradigm. And so, as we think about sort of building devices like these that bring technology closer and closer and closer to us, we believe that employing this level of active learning and looping the human into the feedback equation will eventually enable us to build technology that becomes more human and to some extent more empathetic as well. So that's it. Thanks very much.